Hi everyone, welcome to day 6 of our DSA series. And in today's video, we'll learn how to find the time complexity of recursive algorithms. Okay, so in the previous video, we saw how to find the time complexity of merge sort. Then before that, we saw how to find the time complexity of some generic codes, for loops, nested for loops, etc. And now we'll see how we can find the time complexity of some recursive algorithm. And for example, we'll be taking the Fibonacci series question. Okay, so let us quickly code Fibonacci series. Suppose my question is that I have to find the nth Fibonacci number. Okay, find the nth Fibonacci number. So say I have a function, public, let me give the proper indentation, static int Fibo, here I'll take n. So I need to return the nth Fibonacci number. Okay, so how will I do this? If n is equal to, also, if any of you don't know what Fibonacci number is, then Fibonacci number is nothing but it is a series of Fibonacci series. Okay, so what is Fibonacci series? It is a number series that starts with 0 and 1, and then after this every number is the sum of the previous two. So the third number will be the sum of previous two, which is 0 plus 1 1. Then the fourth number will be the sum of the previous two, which is 1 plus 1 2. Then 1 plus 2 3, then 2 plus 3 5, 3 plus 5 8, 5 plus 8 13, 8 plus 13 21, and so on. Okay, so this is the 0th Fibonacci number, the first Fibonacci number, the second, third, fourth, fifth, sixth, seventh, eighth, and so on. So if someone tells me what is the 9th Fibonacci number, the 9th Fibonacci number will be 13 plus 21, 34. Okay, so here if n is 0, then I'll return 0. Why? Because the 0th Fibonacci number is always 0 and the first Fibonacci number is always 1. So for 0, if n is 0, I need to return 0. If n is 1, I need to return 1. So I can here say if n is less than or equal to 1, I need to return n. Okay. Now I need to call recursion. What did I say? That nth Fibonacci number, my nth Fibonacci number will be the sum of n minus first Fibonacci number plus n minus second Fibonacci number. Okay, the sum of the previous two. So whenever we can divide our question into such manner, we will be using recursion. So I will ask recursion, and recursion is a very good friend of mine, and I will have complete 100% faith that if I just say smaller problem 1 and I say Fibo of n minus 1, so this recursive call will return me the n minus 1th Fibonacci number. Then suppose I say smaller problem 2 is Fibo of n minus 2. This recursive call will give me the n minus 2th Fibonacci number. And then I can say bigger problem is smaller problem 1 plus smaller problem 2, and then I can return bigger problem. That's it, done. This is my Fibonacci number function. Okay, now we need to see how to find the time complexity. So here, if you remember in the previous class, what did we see? In the previous class, we saw that whenever we have recursive algorithms, in case of recursive algorithms, okay, what we need to do is we need to draw the recursive tree, okay, and find the total work done, okay, find the total work done. In merge sort as well, we were drawing the recursive tree, if you remember, and then we were trying to calculate the total work done. In merge sort, the total work done was coming out to be with this formula. The total work done was sum of number of nodes at level I into input size at level I. Okay, so sum of this for every level. Okay, this is what we're doing. Why are we multiplying it with input size? Because if you remember, in merge sort, after calling recursion, we had to call the merge function. Recursion, we used to call two recursions. One recursive call will sort the left half, another recursive call will sort the right half. Okay. And then we need to merge both the sorted arrays. And doing that took big of n time complexity, whatever the input size was. Okay. Whatever the input size was. So whenever I have a whole level, in a whole level, I need to add the total work done for each node. So for each node, at a particular level, the input size is same. So if the input size is same, every node is doing the same job, same amount of job. So I'm just multiplying the total number of nodes at that level with input size. But here, this is in merge sort. This was the case in merge sort. Here, that is not the case. Here, total work done. Here, total work done will be just sum of all nodes for every level. Okay, for every level. So let's see, suppose I call Fibo of 8. Suppose I am calling Fibo of 8. Give me the 8th Fibonacci number. Then this Fibo of 8 will call Fibo of 7, Fibo of 6. Then this Fibo of 7 will call Fibo of 6 and Fibo of 5. Fibo of 6 will call Fibo of 5 and Fibo of 4. This Fibo of 6 will call Fibo of 5 and Fibo of 4. Then Fibo of 5 will call Fibo of 4 and Fibo of 3. Then Fibo of 5 here also will call the same, Fibo of 4 and Fibo of 3. Here again it will call Fibo of 3 and Fibo of 2. Then here 5 will call Fibo of 4. Here Fibo of 3. Here also Fibo of 3. Here Fibo of 2. Here Fibo of 3. Here Fibo of 2. Here Fibo of 2. Fibo of 1. Here Fibo of 3. Fibo of 2. You see how this is spreading, Here Fibo of 2. Fibo of 1. Here Fibo of 2. Fibo of 1. And Fibo of 1. Fibo of 0. Okay. Again, then from here also it will spread. Fibo of 3, Fibo of 2, Fibo of 2, Fibo of 1, Fibo of 2, Fibo of 1, Fibo of 1, Fibo of 0. Okay, and then so on. I think you got the idea. Okay. Now, if you see the left hand side, it will go to Fibo of 2, Fibo of 1, till this. So if you just take a look at this entire big tree, okay, this entire big tree, we just need to find the number of nodes here, that's it. The time complexity will be total number of nodes. Okay. Okay. Now here, what is the height of the tree, or what is the longest branch I can say? This. This will be the longest branch of the tree. You agree? Because on the leftmost branch, it is going from 8 to 1. But on the other branches, it will reach 1. Here, what is the size of this entire branch? Level 1, say call this level 0. Okay, this is level 1, this is level 2, this is level 3, this is level 4, this is level 5, this is level 6, and this is level 7. In other branches, it will reach 1 or 0 before level 7. But let us assume that, okay, in every branch it is reaching till level 7. Okay, let us assume in every branch it is reaching till level 7. Okay, let us assume. So it is a completely filled up tree. Completely filled up tree. That is our assumption to make the calculation easy for us. So what we'll do is, in level 0, how many nodes are there? 2 power 0. In level 1, 2 power 1. 2 nodes, isn't it? In level 2, 2 power 2. In level 3, 2 power 3. In level 4, 2 power 4. In level 5, 2 power 5. In level 6, 2 power 6. In level 7, 2 power 7. So the total number of nodes. So the total number of nodes will be, suppose whatever my n is, say my n was 8. So the last level will be 7, which is n minus 1. So the total number of nodes will be 2 power 0 plus 2 power 1 plus 2 power 2 plus 2 power 3, like this till 2 power n minus 1. Okay, and this is the sum of GP. This is a geometric progression. So if you guys know what is the sum of geometric progression formula, it is usually something like this: a into r power n minus 1 by r minus 1, where a is the starting point, r is the ratio which is getting multiplied, and n is the number of elements in the entire series. So a is 2 power 0, this is the first element, r ratio is 2, that is getting multiplied at every other term, n is total n minus 1 by r2 minus 1, 2 power 0 is 1, so this is 2 power n minus 1 by 2 minus 1 is 1, this is 2 power n minus 1. That's it. Total number of nodes is this. So my time complexity also becomes big O of 2 power n minus 1. And when n is too big, 2 power n is also too big. We can remove 1 in comparison to that and directly say the time complexity is big O of 2 power n. That is why in this question, to find the nth Fibonacci number, the time complexity becomes 2 power n. Now, once you learn dynamic programming, you will learn how to convert this code in a much more efficient way, where we go from 2 power n to directly big O of n time complexity. Okay, but I hope now you understand how this is working. You might have got that vision. Similarly, if you go to LeetCode and search for the staircase problem, there the time complexity is 3 power n. But I hope now you don't have to mug it up. And you can visualize and you can think why it is 3 power n, here why it is 2 power n. Okay. So that's it for today's video, and we'll see you all in the next video on day 6 of our DSA series. But if you want to learn these concepts in a much more in-depth manner, for example, how this formula is coming and a lot more complex things, then do join CodeKerdos.